Yes, so the topic I was given more or less was to tell you how to make fMRI more repeatable. Well, I'm from the Faculty of Psychology, so I will first depress you and then build you up again. So that's the plan. So how it all began, you probably have seen that before. I couldn't attend the morning, but it started about 30 years ago, and Ogawa was one of the pioneers. And I was happy to meet him some years ago in Trondheim, which was a nice occasion. That's how it began in Bergen, actually, in '94, so quite only some years after it was invented, and I came into the fMRI business in '95. So, and that was actually a pioneering time, because we did a lot of stuff, a lot of things that didn't work, but that gave you also a feeling of what fMRI actually can do and what it can't. So, and that somewhat put me on the path of looking at how fMRI actually, how stable it is, how repeatable it is. So what do we have? So already in the start, fMRI was thought of being a very good clinical tool, but as also Frederick was into it, it's still only on the pre-surgical mapping level. It's still not capable of doing some diagnostics, for example, in psychiatry and those things, which we were perhaps would also be more interested in. That actually, some of those mappings I did quite in the start. So we did quite a lot of pre-surgical mapping already in the late 90s. Actually together with Andreas Bartsch. Insider joke. And we did motor mapping, language mapping, and as Frederick was also into, we did also mapping with different functions to basically surround the tumor, for example, to see where are the borders also functional-wise. So no patient actually went into the scanner with only one paradigm. We typically did a combination of those. And why were we doing that? Well, it was not only pre-surgical mapping we were interested in, but also for example, post-stroke mapping to see what's a gain after a stroke, to do some mapping there. And those who are familiar with stroke patients know that if you have seen one patient, you have seen one patient. The next one is completely different. Different lesion, different functional areas activated. So that's something that we actually also wanted to see and work further on. But if you go into the depths of what we actually have, it's that a lot of things work quite well on the group level, but of course we would like to have single level results in our studies, so that we can make also prediction for the outcome, for example, especially in those patient groups. And perhaps also selection of therapy. So the ultimate goal is basically to go to some kind of individualized therapy, precise medicine based on fMRI results. So it has been the goal 30 years ago, and unfortunately it's still the goal, because we are still not there. And there was an interesting article some years ago that had this interesting title: "Why is clinical fMRI in a resting state?" which basically has as a topic why we are still doing only pre-surgical mapping with very simple paradigms, simple motor tasks, simple language tasks. And those who would like to read it, it's from these authors. And I will try to guide you a little bit through the problems that we have with fMRI and how we hopefully can solve it in the future. And I will separate it into 4 different aspects on at least the factors that compromise reliability of fMRI studies. One is how we actually design our tasks, how we conduct fMRI. One would be on the MR systems, one on the fMRI type of analysis, and one on the physiology of it. So starting with that. I guess you're all familiar what fMRI is actually about, what it rests on, but it's always good to get a reminder a little bit on that, or what we are actually talking about. We are interested in the effect of our stimuli on the brain, and to see what the brain response is, how and where the activations are. But we actually have a long cascade of different processes that have to happen before we actually, here at the end, can get a very tiny fMRI signal. So the signal, of course, can get lost somewhat on this path from up here to down here. You also have some biological factors that make a sharp signal into something that is stretched over several seconds. And along with that is basically also an increasing level of uncertainty based of signal noise, of physiological noise. So only when everything happens, you get an fMRI signal. Which also means in return that if you don't get an fMRI signal, you can't say that nothing was happening here. It might be that through perhaps a badly selected design or through some other aspect, the signal somewhat got lost. I also observed in some of the pre-surgical patients that I scanned, 30 years ago, but I guess the effect is still there, that some patients have a negative board signal around the tumor because the vessels or the physiological system is not functioning as in a healthy brain. And if you use, for example, tools that only look at the positive board signal, you probably will never see that there is actually activation. And that comes because when you have a brain activation, you have increased need of oxygen, which means the blood flow increases. But if blood flow does not increase, and you still have an increase of need of oxygen, you actually get a decrease of the ratio of oxygen and a negative board signal. So just to make you aware, if you don't get something, it does not mean that there is nothing. It might be that it somewhat got lost, or it might be a negative signal, or whatever. So only when you get an fMRI signal, you can basically somewhat assume, yeah, there seems to be some activation. So conclusion is basically only going into one direction. And if you think further, what is a board signal based on? I typically call it a metabolic echo, because it's basically an echo that is generated by a complex physiological mechanism that then finally ends in something that you can measure with your MR machine. So that you have increase of blood volume, increase of blood flow, increase of oxygen extraction rate, and that accumulates somewhat into the board signal that you actually can measure at the end. So far, so good. The problem is that all these processes are affected by quite many other things. For example, blood pressure has an effect on it, heart rate variability has an effect on it, how much coffee you had before the scanning has an effect on the blood pressure, but then has an effect on the board signal. Level of cortisol and other hormones has an effect of it. And on top of it is also the circadian rhythm, which means the board signal also varies over the day. And we actually did a quite extensive study recently that is still under, or we're still analyzing the data and trying to put things together, where we scanned the same subject at different time points of the day. And we based that study on some pre-analysis from the Human Connectome project data, where we downloaded data from almost 600 subjects. Sorry for the very busy slide, but the main part is actually down here, because it shows you the variation of the bolt amplitude over the day, and it's somewhat, we only had data between 9 o'clock in the morning and 9 o'clock in the evening, but you somewhat have, from a distance at least, the idea of a kind of circadian rhythm in here. So the bolt signal varies over the day. And then we already scared some of our clinical colleagues because they scan their patients during daytime and the control subjects in the evening. And of course, you might get some results of that. So that's something you at least should keep in mind. But as I said, there are also many other effects. We for example, in one study, we also collected the blood pressure prior to the scanning time, and that also correlated a little bit with the bolt signal. Because what you have to imagine, it's a blood volume effect, and that comes from the vessels being elastic. But that varies over the day, and that also varies with the blood pressure. So if they're very stiff vessels, then you get a complete different dynamic in the bolt signal. So the bolt signal itself is a very noisy signal, and it's influenced by many endogenous and exogenous individual parameters. So to get reliable single subject data is kind of challenge. Coming to the fMRI design, that's the dynamic we are dealing with. So if you, let's wait another cycle. So if you focus here, you get the stimulation, and now you have a bolt signal. So the stimulus is already gone, and the machinery is still running. Which also has some limitations on the temporal dynamic of fMRI. And also how you perceive those stimuli. So you probably observed this as a very intense stimulus. And it is a very intense stimulus, so that's no question about that. So we did a study where we just run a couple of subjects and gave them instruction, well, just ignore what's happening on the screen. Although this is a very intense stimulus, just ignore it. Just think about something else. Keep your eyes open, of course, but think about something else. Focus on it, and focus on the target stimulus. You probably noticed that there was a letter somewhere in there, and we varied it, and so they had to react to it. If you look at the group data, that looks quite nice. Independent of the instruction, they did on the group level the same results. But we just repeated the same stuff a few days later and looked at how identical is on the individual level the activation. So red is good, yellow is, and green is bad in this color scheme. So if they had the instruction to ignore it, they did something completely different on the 2 days, on the individual level. On the group level, it looks still fine, but on the individual level, the amount of activation, perhaps the localization varies a little bit. So this shows that there was a very huge variability from one day to the next. It was much better when they had to attend. Surprisingly, discriminate didn't work much better, but just giving the instruction to attend to the stimuli actually gave very reliable result. And the point why I'm saying this to you is that instruction to the patients is a very important thing. They can ruin your entire result, but just by giving them the wrong instruction or distracting them to something completely else. So that's why we often write down our instructions so that all subject that went into the scanner gets exactly the same instruction. Not telling one story on one day and another story on another day. Because that creating expectations, creating some idea of what the study or the paradigm is going to be, can generate completely different activations. So instruction is a very important thing. Frederick was a little bit into that. You typically have two tasks. You have to have at least two tasks, because that's the other thing you have to keep in mind. fMRI is not a measure of total brain activity. It measures the change from one state to another. So you need two states. So which in our terms means you need two conditions. And these two conditions have to differ, at least in the parameter you're interested in. Like, for example, auditory language task and the auditory control condition, where you subtract the auditory sensory input and you're left with language activation. But if your control condition is too close to your experimental condition, you're probably subtracting away everything. So the subject or the patient can work like hell in the scanner and you will get completely nothing, because there's no variation from one condition to the next. So thinking about what type of activation actually my control condition generate is also a very important process in creating a clinical paradigm. Because you have to provoke a change in the board signal from your control condition to the experimental condition. The best paradigm for it is block design, where you have a couple of stimuli over a certain period, and you can sum up over this period. So block design is a very efficient design and gives you very good signal-to-noise ratio. It's easy to conduct, and it's easy to instruct also for the patient. So that's basically the recommended design for clinical applications. Here you see it from some data where you see that there is a good separation between the control condition and the experimental condition. The question is now, how long should these periods be? Could they be of any length? Where the recommended length is somewhat between 20 and 40 seconds, because you have to consider the board signal is quite smooth. It has a very long tail that goes over many, many seconds. So to get down to the baseline, to have a good separation between your baseline or control condition and your experimental condition, each block should be at least 20 to 40 seconds. If the blocks are closer together, you probably don't reach the baseline anymore. And then your signal change, which is your board signal, gets smaller and smaller. An alternative, of course, is always resting state that became somewhat popular in the recent year. I'm a bit critical to that, as you might have thought. So resting state, for those who are not familiar with that, is running fMRI without a paradigm and just looking at the fluctuations that occur. And these are not random fluctuations. They are somewhat show a very spatial temporal characteristic. So that's why resting state became somewhat into the focus, because it doesn't necessarily need an instruction besides either close your eyes, keep your eyes open, or look at the fixation cross, or sometimes you also have some arbitrary slow moving things on the screen. But you have to keep the instruction constant, because each instruction already gives a different result. So if you would like to have comparability, you always should keep use the same instruction. But what happens then is that the board signal fluctuates very slowly with frequency below 0.1 hertz. And in the analysis, you will cover these fluctuations. And what has been found is that these fluctuations have a very spatial temporal characteristic that looks very similar to functional networks. So if one compares fMRI results from tasks where subjects actually were doing something, and where one did resting state and extracted these resting state networks, you see that you will find resting state networks that are very similar to those networks that actually are activated when subjects are performing a task. And that makes resting state kind of interesting in a way. But the problem is that it's not a structured information exchange in a way. So we looked at some network models where a subject actually performed a language task in this case. So we had some sensory activation, we had some directed connectivity, we saw activity in that what we call the ventral stream, we saw a little bit activity in the dorsal stream. And if you look at the exact same network in resting state and do a connectivity analysis there as well, you see that everyone is talking to everyone. It's not a structured information exchange in the network anymore. So that's what you get with resting state. And the question is, does it really tell you something in a clinical context? So that's why I would be a bit careful in using resting state in a clinical context, as long as we do not really understand what's going on there. The MR system itself, of course, also generates some noise and is a source of variability. For example, you have occasionally some local instabilities. We did some reliability measures for perfusion ASL perfusion measures, and we saw that it looked very good on the left hemisphere, but on the right hemisphere we had a lot of variation in a particular area of the brain, which is not visible on a single data, but if you just do a proper analysis, you probably will catch that there might be some area that is not picked up by your daily quality controls, but still shows some variability. So one also has to be somewhat keep that in mind, that the system is perhaps not as stable as you think. And of course, field homogeneities, especially on 7 Tesla, where you have very bright signal in the middle and darker to the outside, that needs to be compensated. So that's also something one has to keep in mind. Last thing on fMRI analysis. A typical fMRI examination collects quite many data. It might collect the structural data, it might collect the fMRI data. What we typically do is also that we collect ASL perfusion data and diffusion tensor imaging, and perhaps also MR spectroscopy. In the daily routine, you have a protocol that probably looks like that, with some structure, with some functional measures. And for each of the modalities, you have your own analysis pipeline. But you're not typically performing any analysis that actually combines all these things. You are analyzing the perfusion on itself, you analyze the fMRI on itself, but perhaps the perfusion could inform the fMRI analysis because of the issues what I told you before, because of the variability in the blood flow, blood pressure, stiffness of the arteries, etc. So that's something we are kind of working on, how to combine that. And that might be the next step in especially the clinical application of fMRI, to combine more of those information that you actually collect. For example, combining or putting in the perfusion measures, to put in certain structural measures, etc., that can inform then a coherent analysis of the fMRI data to make it more reliable, to make it more stable. So to summarize, is it that bad? Well, that was a depressing part in the beginning, but I hope ended on a more positive note. So the main point is that one has to be aware of the limitations. So fMRI is not just run through it and everything is perfect. You have to be aware that things are not necessary in the way you think. There are now very good and very efficient paradigms that are able to generate very reproducible fMRI results, but we are still on the level of pre-surgical mapping, but we would like to get beyond that at one point. There are a couple of initiatives going on how we can combine all these different modalities. AI might be a keyword in this context as well, to combine as many information in a very efficient and automized way. That's something that is especially for the clinical purpose of relevance, that those who are going to analyze the data don't have to click in 3 days to get the result. It should be facilitated in a way that it can be integrated in a more automized way to make fMRI available to a broader clinical application. And with that, I thank you for your attention.
Thank you very much. Any questions for Karsten? Yeah.
I have a question. I'm not sure if it's that relevant. You have shown a slide where you found this variability, right? So people who have some kind of brain issues or cognitive issues, they take some kind of medicines like antidepressant or antipsychotic medicines. But do you think this kind of medicine, because they cross the blood-brain barrier and have influence the brain activity, modify the brain activity? So do you have this kind of medicine can affect the MRI imaging?
As far as
if a patient uses a drug before taking the MRI image, or if the patient is already in medication for long, and how it will affect the MRI?
well, there are certainly some drugs that influence the fMRI signal. I can't list now which one does and which not, but that definitely a contributing or a factor that contributes to the variability between patients.
Yes. Yeah, I have a question. So when we say drugs or any external conditions, physiologic conditions that might affect the fMRI signals, I think we mean the whole signals in general.
Yeah.
But since we do rest with compared to task, so do you think this might be the solution that might compensate for any, if the blood pressure is high, so it's going to be high during the task, that's going to be high during the rest as well. So do you think this could be...
They can affect the dynamic of the blood signal, because they might have a vascular effect on the arteries, that they do not widen as they typically would do in a healthy subject. Then you get a much higher blood flow because the arteries are so stiff. So the effect might be there. So it might not affect very much in the way you describe it, and you probably will still see some changes, but you probably will see differences between one patient and the next that is based on the drug.
Okay. Just another question, from my curiosity. Do you think if the people who are making software for this image analysis, is there any way that they can measure the effect of the drug in the blood fluid volume or any effect, and they can subtract that specific data from the overall data to make the data analysis more precise?
I'm not aware that any software does that already. We're working perhaps on that. Just to tell the story, so what we did recently is a study where we also collected blood samples to exactly see what parameters from the blood could be relevant to improve the fMRI signal. But that, for the moment, it just created some creative programming. I'm not aware that any software does include and compensate for those things automatically if you have those information. But that's basically what I mentioned at the end. Combining those information is my hope that this might be something for the hopefully near future to get integrated.
Thanks for the presentation first, and great slides, by the way. We want to say that. But when it comes to the combination of these different images and imaging modalities, or like paradigms that there are, is there some kind of resource where I could, for example, like read about that? Because I don't have an idea right now how you would combine perfusion images with fMRI, with like bold images, or using the other images which were acquired. Is there some kind of resource publication which already talks about that?
I'm not sure. That's at least something that we're working on. I haven't seen that in that way yet. We kind of prospectively collected all these data in quite many studies in the hope that we, at the end, can integrate it. But I haven't seen a study yet that actually, for example, integrated perfusion in an fMRI analysis. But hopefully it will come soon.
Thank you.
Daniel?
Thank you for the presentation, first of all. You spoke about explaining the patients before doing the fMRI exams could influence the results. Is there any specific way that you do that achieves the best results that you recommend?
No, besides keeping it constant, so that every patient gets the same instruction. That is perhaps the best advice. In scientific studies, we sometimes differentiate between things we tell our research subjects and things we don't tell them, not to generate some prediction and expectation, because expectation already can generate activities that you don't want. But in a clinical context, I think just keeping the instruction constant is the best way of having at least a kind of stable
So would you
result.
recommend not showing just the instructions beforehand, or just explaining verbally?
No, I think the best way would be to explain it as good as possible beforehand, because being inside the scanner, it's completely stressful for the patient.
Because some centers use like flashcards that they should.
I think that's perfectly fine. Yeah.
It doesn't raise expectations, or just prepares them beforehand.
It depends on the paradigm, but I think for most of the paradigms that are used nowadays in clinical context, that's perfectly fine.
Thank you.
One more.
Sorry, I haven't been that much on this side of the room, actually.
So you talked about your uncertainty towards resting state for clinical, but then you can use functional connectivity in the task. So there you would be engaging the brain regions that are supposed to be engaged in the way they're supposed to, but then having a different perspective, so to say, on the brain activity. So how do you think would that be in the perhaps near future more move towards clinical application? Because currently it is widely used, but in the research.
Yeah. Well, I hope that's something that also will get more and more popular, or not popular, but more available also in the future, as we get more and more to know how network connectivity actually looks like and how it's affected by certain disorders. And then that brings perhaps different clinical populations into the scanner if you don't look at the brain activity, but at the connectivity as a measure. But we are not there yet. But, I hope that we will get there, perhaps in another 30 years.